So I don't think I can use this while uh,
Okay, stop. Stop.
Okay, let's get started in a couple of minutes. It's 6 o'clock right now. Okay, everyone. Um, let's get started with today's session. Hi, I'm Shankar, and I'm the TA for the teaching assistant for this course on fluid and particle mechanics offered on NPTEL by Professor Sumesh and Professor Basavaraj. These are weekly interactive sessions happening on Monday from 6 o'clock to 8 o'clock for students who have registered for this course or who are interested in this course to put forth their questions and ask doubts. We'll be doing some problems every week. And with that, let's get started. First, we'll finish off the assignment questions that were due earlier. So the week 2 assignments will be discussed here first. So most of the questions are on fluid flow problems where it's on UR, U theta, and the Navier-Stokes equations and the Bernoulli's equations. I think there will come a Bernoulli's equation as well. And there's also a question on this particular question exactly is on the Newton's law of viscosity, and we'll also have a discussion on a few of the practice problems that was there discussed in the week 2 assignment questions, and also a couple of questions on the current week, on week 4, based on the non-dimensional analysis and the Buckingham pi theorem. If you have any questions, please feel free to stop me during my while I'm talking and ask your question whenever you want. So let's get started with the first question of the graded assignments that were there for week 2. This question deals with a block of weight W that slides down an inclined plane while lubricated by a thin film of oil, as shown in figure 1. The film contact area is A, its thickness is H. Assuming a linear velocity distribution in the film, derive an expression for the terminal or zero acceleration velocity of the block. If the terminal velocity of the block is 15 meter per second, the mass of the block is 6 kilograms. Area is 35 centimeter square, and the film thickness is 1 millimeter, 1 millimeter thick. Oil of viscosity is used here as 0.29 kilogram per meter second, and density is 891 kilogram per meter cube. What is the inclination of the plane? Theta. And we've been asked to report the value in degrees, so that the marking can be more accurate. So let's get started with the solution of that. What we do here is first just take a balance or a force balance of the center of mass of the block, and we know that block is having a gravity component in this direction. And we can resolve that gravity component into these two directions. If this is theta, then we know that this is theta, and if this is theta, the component of gravity in the motion of direction of the block will be g times sine theta. So with that thought, let's just find the gravitational force is given by the weight of the block or the mass of the block times gravity times sine theta. And as I had mentioned earlier, if the block is like this, that is experiencing a center of mass gravitational in this direction, and if this direction and this angle would be theta, if this angle is theta, therefore this can be, the gravity can be resolved into g cos theta and g times sine theta. And that's where we get the force in the direction of flow to be W times G times sine theta. Although this is the center of mass velocity, we can still approximate same force over here throughout the block, actually throughout the block. Therefore, what is being opposed is actually the is actually the thin film of oil that's present over here. So this block is on in between a film of oil that's on an inclined surface. So that block will be offering some resistance. So the film of oil will be offering some resistance, and we know that the resistance offered by the oil will be can be written down with the help of Newton's law, and that's given by let's call that force as the force offered by the oil, as it will be equal to the shear force or the shear resistance that is offered by the oil on the block, should be equal to the Newton's formula, that means mu times du by dy, but this should be just the shear stress of the oil, or sorry, there's no w, there's just tau, and that times the area will give you the force of the shear resistance. And since it is given that there is a linear velocity distribution in the film, and this is very crucial because if that is the case, then we can just write du by dy as mu times v by h times the area. This comes from the linearization of velocity in v and h. And yeah, so basically what happens is u is equal to, since we have to take a linear approximation, we can write as c1 plus c2y. You know the boundary condition y equal to 0, u is equal to 0. This is known as the no slip condition. And we know that y is equal to h, u is equal to capital U. That's given in the question, or that's capital V. Sorry about that. Capital V. And this is given in the question. Therefore, just by substitution, you can just get that u is equal to Vy by h. And this du by dy is evaluated at the block interface. And therefore u will be equal to v. That's again a part of no slip condition as well. Since the block is moving with the velocity v, we assume that the layer of oil that's closest to the block will also move with the same velocity. That's also part of the no slip condition. Now, since we have established this much, we can just move forward and substitute. We can move forward and equate the gravitational force to the shear resistance, the force offered by the shear resistance, and we can just get that W times G times sine theta should be equal to nu times V by H times the area. And what we need to find here is, in fact, the inclination of the plane, or we have to derive an expression for the terminal velocity, and then figure out the angle of inclination over here. So we just rearrange this to write V is equal to WGH sine theta by mu times A. And we can find out theta as sine inverse of the whole term. Mu VA by WGH. Now, what all has been given here? We know that the velocity is 15 meter per second. Therefore, velocity is 15 meters per second. The area is 0. Sorry, let me just take a look at that. 35 centimeters square. And that is 0.0035 meters square. Viscosity, I think, is given as 0.29. Yeah, viscosity is given in SI units as 0.29. So we can just use 0.29 kilogram per meter second. And the weight of the block is 6 kilograms. The gravitational constant is 9.81 meter per second square. And the H refers to the film thickness, that's 1 millimeter, which is 10 raised to minus 3 meter. And just substituting in this, we'll get theta is equal to sine inverse of 0.29 times 15 times 0.0035 by 6 into 9.81 into 0.001. And this is a fairly easy calculation. I am hoping that you would be able to get the answer that I got, which is actually 15 degrees. Again, I may be wrong. I may have made a mistake in my calculation, but I am hoping that if you can verify the answer, I'll be grateful. I am hoping that I am audible to the people in the audience. I don't even know if you joined. Yeah. Okay. Thank you, Mike, for your response. Just give me 1 second. I'm just trying to adjust a little bit on my computer. Okay. So yeah, we'll get theta as 15 degrees. So the answer is 15 degrees over here. Now we'll move on to the next question. Question number 2 of the second week's graded assignments. Whereas given that the fluid flow in a lubrication film can be understood by analyzing the Navier-Stokes equation, but under certain approximation. For example, figure 2 shows a part of a region where a fluid is sandwiched between a moving wall with velocity u, this is the moving wall on the bottom side, and a fixed slipper block, and this slipper block is shown over here. Let the lubricating oil be viscous and has a density of rho and mu. So there is oil of viscosity rho and mu in the gap between them. Unlike the previous problem here, the height of the oil film is not constant. So we can see that there is a tapered, the fixed block is tapered, and therefore film thickness will change with x. However, if the gap is thin, h is very much less than n, it can be shown that the pressure and velocity distributions are of the form P is equal to P of x and U is equal to U of I and V and W are equal to 0. It's given that U and V are equal to 0. Neglect gravity, reduce the Navier-Stokes equation to a single differential equation for U, and what boundary condition will you use to solve the problem? Integrate and find the expression for U. Okay, so what we have is fairly straightforward, where we just need to write down the Navier-Stokes equation, which can be written down in the Cartesian coordinate as let's start with our unsteady term dou u in the let's just take the x momentum equation. Since this is in the x direction, we'll just take the x momentum equation, and that is given by dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Now we equate this to the differential pressure dou p by dou x plus the there's a 1 by rho term over here. Now there is also the viscous term that's given by mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus gx, the term associated with gravity over here. Now we'll just see which all terms we can neglect. We can assume a steady state approximation. Therefore, this goes to 0. We know that v and w are both equal to 0. And we know that u is a function of y and not a function of x or z. Therefore, this term goes to 0. This term goes to 0. This term goes to 0. It's also given that we can neglect gravity, and so therefore this term goes to 0. So finally we'll get the equation as minus dou p by dou x plus mu dou square u by dou x square. This is actually mu by rho, in fact. So we can neglect the rho terms over here in both the sides. We get minus dou p by dou x plus mu d square u by dx square should be equal to 0. All we need to do is integrate this twice. We still have the condition that the pressure is constant. Oh, sorry, pressure is a function of x as shown here. So we just need to integrate this part, assuming that the differential pressure is in fact constant. Although it's given that p is a function of x, we just have to assume that dou p by dou x comes out to be a constant. It's linear variation of pressure in the x direction because of the tapering that's just over here. So when you rearrange this, you'll get mu d square dou square u by dou x square should be equal to dou p by dou x. Integrate this once, you'll get mu into dou u by dou x should be equal to oh sorry, so sorry about that. This is not x, this is y. But the pressure is a differential of x, so when you integrate this, you don't have to worry about integrating pressure in the x direction, in the y direction. So you'll get again a little bit of rearrangement. You'll just write this as 1 by mu. Then you can integrate this and say minus 1 by 1 by mu dou p by dou x into y plus c1. Integrating this again, you will get u is equal to 1 by mu dou p by dou x y square by 2 plus c1y plus c2. Now we have a differential equation that has been integrated to get an equation for u. All we need to do is apply the boundary condition. Now, what boundary conditions do we use here? Okay, it's said that the bottom wall is moving at a velocity u. Therefore, we can use that condition, and we can assume that u is 0 at the bottom wall. Sorry, the y is 0 at the bottom wall. So therefore, boundary condition number 1, y is equal to 0. We get the velocity to be equal to u. I think it's u. Sorry. Yeah. And second condition is the second boundary condition is whenever there is we are dealing with the block on the upper surface or with the fixed slipper block. Let's say that that is at a distance h of x apart, and whenever we are dealing with that, we know that due to no slip condition, this velocity will in fact go to 0. Therefore, we can say that y is equal to h of x, which I am also denoting as just x from here on. We'll get u is equal to 0. This is at the top and this is at the bottom. We don't have to worry about h being a function of x, since u is only a function of y. Okay, so this will be boundary condition number 2. Now we have two boundary conditions. We just have to substitute them. We'll get by putting the first one, we'll get C2 as u. And by putting the second one, we'll get 0 is equal to we'll get 0 is equal to 1 by mu dp by dx into h square by 2 plus c1h plus u, since c2 is u. Therefore, just by rearranging, you will just get this as 1 by minus 1 by mu dp by dx h by 2 plus u by h. And substituting this, substituting the value of c1 and c2 on this main equation, we'll get it as u is equal to 1 by mu dp by dx into y square by 2 plus minus u by h minus 1 by mu dp by dx into h by 2 times y plus u. And this is the first term plus c1y plus c2. Let's not c here, this is actually u here. And a little bit of rearrangement, and we'll get the answer as, sorry for that. We'll get the answer as 1 by mu dp by dx times 1 by 2 times y square minus yh plus u times 1 minus y by h. And this is the final answer that we get. Yeah, integrate and find the expression for u. This will be the final expression for u. I don't remember an option being given to this question, but I think there is an option for this. I think this is the right answer. I have not just written down the options. Okay. If you have any questions, please feel free to let me know. I'll be happy to answer. Let's move on to the next question. Consider the simple incompressible flow pattern U is equal to capital U, V equal to 0 and W is equal to capital W, where U and W are constants. This is crucial here. Convert these velocities into the cylindrical coordinates UR, and theta is defined from the x direction. Therefore, we'll get, we know that from the discussion that was going on in class, if we have to write u r in terms of x and y, we'll have to write this as u times cos theta plus v times sin theta. And u theta would be equal to minus u sin theta plus v cos theta, and uz would essentially remain as it is. This is for the cylindrical coordinates. Therefore, we are only required to find out what UR is. Therefore, UR would be U times cos theta, that is capital U times cos theta, plus V sin theta, that would essentially be making it 0, since V is not there for this question. Now, I think all other questions have to be are answered in the same way, where the next part of the question is U R, U theta, and U Z. We just have to find them out and then move forward. So we can write U theta as minus U times sin theta, and we can write U Z as just blue. Okay, next we have to find out the we just have to find out whether they satisfy the continuity equation in the cylindrical coordinates. And how do we do that? We need to first write down what the continuity equation in the cylindrical coordinates is, and that's given by 1 by r times dou by dou r of r times ur plus 1 by r times dou by dou theta of u theta plus dou u z by dou z should be equal to 0. This is for the steady case, and it's assumed that it is steady because there's no time dependence anywhere shown in the equations for velocities. Now what we have to do here is differentiate ur with respect to r, and that turns out to be 0. Therefore you will only get 1 by r times dou by dou r of r times u times cos theta plus 1 by r dou by dou theta of minus u sine theta plus dou w by dou z should be equal to 0. And we know that this goes to 0 because w is a constant. Therefore, the equation would come out to be 1 by r into u cos theta minus u by r into differential of sine is cos. Therefore, u by r into cos theta, and which would in fact get it as 0. Therefore, we can say that the equation of continuity is satisfied. Okay. Next, it will be as another set of questions based on a small introduction. Consider an incompressible flow at a volumetric flow rate Q toward a drain at the vertex of a 45-degree wedge of width B as shown in figure 3. So this is the figure that's shown. What it means is that this is a place where there is flow between 0 to pi by 4, and this is a drain. So there is a flow from here to here. You can assume that this is a wedge or a narrow space near the end of a room, and this is actually a drain, and that's there at the end of the room to drain out the water that's coming. So water is coming in this direction, and this water that's coming is a function of radius and not a function of the angle over here. It just depends on at what point of in the radius we are looking at. It doesn't matter where we are looking at like this. It only matters where we are looking at in this direction. So let's get started. If we say that the flow is purely radial, which of the following is a correct expression for the velocity profile? And if it's purely radial, we know that the flow rate is defined by velocity times the area. And here the velocity is ur, and the area for a wedge is given that it's 45-degree wedge over here, and wedge is basically it has the z component that is constant, so we just write that out here, or we'll just give it a term h over here, and the other area and the other part would be in fact taking the form of a circle. So the area of this part would be in fact pi by 4 times r. Let's assume that if this were a complete cylinder, its area would have been 2 pi RH. But since this is not the case, since it doesn't go from 0 to 2 pi, we'll only get pi by 4 times r times h, since this goes from 0 to pi by 4. That's how we get this area to be pi by 4 times r times h. Now if we define q as the volumetric flow rate per unit width, or we'll just put a prime over here so that we can able to differentiate between those two, you can get that ur is equal to pi by 4 times r. Therefore, you can write ur as 4q by pi r. And among the options that's given, ur should be 4q by pi r. That's there in option B, D, and E. But since the flow is purely radial, u theta and uz should both go to 0. The only option that matches that is in fact option B. Therefore, the correct answer is option B. Option B, yeah. Okay, moving on. Question number 6. The velocity profile obtained in the previous question will violate which of the following? It will be the no slip boundary condition on the walls, no penetration boundary condition on the walls, equation of compressibility, or all of them. The correct answer for this question is, in fact, I'll tell the answer and then explain why it's so. It's actually the no slip condition on the boundary condition on the walls, because ur is not equal to, so if we take ur at this point, we know that it should be 0, but that is not the case. There is some flow even at near the radius. Therefore, the no slip condition won't be satisfied. Therefore, the answer is A. The no slip condition, I mean, on the no slip boundary condition on the walls will not be satisfied. The no penetration condition will be satisfied if there had been a u theta, but since that is not the case, since u theta is equal to 0, this is valid. Since u are not equal to 0, this is invalid. And yeah, we don't have to worry about the equation of incompressibility anymore. Okay, same question. Simplify the viscous term in the R momentum expression and find it. So the viscous term in the R momentum equation refers to the term that's associated with the viscosity mu in the cylindrical coordinates, and as given has been asked for the R momentum. So let's write down the R momentum equation first. In the cylindrical coordinates, that can be written as rho times dou ur by dou t plus ur dou ur by dou r plus dou u theta by r plus dou u r by dou theta plus uz dou u r by dou z minus u theta square by r. should be equal to minus dou p by dou r plus mu into 1 by r dou by dou r of r dou u r by dou r plus 1 by r square into dou square u r by dou theta square plus dou square u r by dou z square minus u r by r square minus 2 by r square into dou u theta by dou theta. And we know that ur is a function, ur is 4q by pi r, u theta should be equal to 0, uz should be equal to 0. And so let's cancel out the terms that does not exist. This is 0, u theta is 0, ur is not a function of theta, uz is 0, u theta is 0. Oh, we don't have to, we are not concerned with that right now. So we don't have to, neglect everything right now. We just have to find out what the viscous term in the R momentum equation is. So we just have to equate this part of the equation, and it can be written that again we can simplify this part of it. Ur is not a function of theta or z, and u theta does not exist. So we'll get this part as 1 by r dou by dou r of r times dou by dou r of 4q by pi r, and minus ur by again ur I'll write it out, 4q by pi r times r square. So we'll get this part as 1 by r dou by dou r of minus 4q by pi r. I just skipped a step over there so that, okay, in fact I'll not do that. You'll get r into, what is the differential of this? You'll get minus 4q by pi r square. And we know that this r and this r square would get cancelled, minus 4q by pi r cube. And you'll get this as 1 by r times 4q by pi r square minus 4q by pi r cube. And this will in fact yield 0 as the answer here. Okay, so let's move on to the next term, and it's asked how to simplify the term, viscous term in the theta momentum expression and find it out. So first let's again start with the theta momentum balance, and that can be written out as rho into dou u theta by dou t plus ur times dou u theta by r plus u theta by r times dou u theta by dou theta plus uz times dou ur by dou z Oh, sorry, this is not UR, this is dou U. Theta by dou Z plus UR U theta by R is equal to minus 1 by R dou P by dou theta plus mu times dou square 1 by R dou square by, oh sorry, 1 second, mu times 1 by R dou by dou R of R dou U theta by dou R plus 1 by R square dou square U theta by dou theta square plus dou square U theta by dou Z square plus 2 by R square into dou UR by dou theta minus U theta by R square. Again, in these expressions, there's also the term for gravity that I have completely neglected, assuming that there's no gravity over anywhere. Anyways, we are only concerned in the viscous term that's appearing over here with mu, and let's focus on finding out what all gets cancelled. Wherever theta comes, it will automatically go to 0. So all of these terms have a theta in them, and therefore this we can directly write it as 0. Yeah. Okay, just wait a minute or two for you to catch up. Before I do the next question, I'll take a 2 minutes break here. Okay, so let's get started. Let's resume what we've been doing now and go to question number 9 of the week 2 assignments. Okay, if it is given that P is equal to P naught at a radius R is equal to capital R, what would be the pressure that develops at any R corresponding to the radial flow? So let's again go back to the R momentum equation, and we have already taken out some terms that are associated with the viscous term. and we saw that the entire viscous term is in fact going out to 0, so we don't have to worry about this much. Now in the convection term, we just have to cancel out a few more over here. We know that it's a steady state process, u theta is 0 and ur is a function of r. Therefore these many terms get automatically vanish, and we can write the momentum balance as as ur is equal to ur into dou ur by dou theta, dou ur by dou r should be equal to minus dou p by dou r. And just do a small manipulation and we can rewrite this as dou by dou r of ur square by 2. If we take the differential of here, we'll get the term that has been written down over here is equal to, or we'll write this as plus dou p by dou r is equal to 0. And this equation is very famous in our chemical engineering, which is famously known as the Bernoulli equation, or the point form of Bernoulli equation, where it is evaluated at a point. Now if we integrate this, we'll just get ur square by 2 plus, or u1 square by 2. Let me rewrite that as u1 square by 2 plus p1 should be equal to u2 square by 2 plus p2. Now we can now uh, apply the boundary condition that at r is equal to capital R, p is equal to p naught. So let us assume that second. Let us assume that at p naught we have u capital R square, and at p of r we have u small r square by 2. And we'll get this as ur we have written down earlier in our earlier expression over one more question, 4q by pi r. So u capital R will be 4, not be 4, you have to square it, it will be, I'll write it as 4q by pi r the whole square. It's equal to p of r plus 4q by pi small r the whole square times 1 by 2. Therefore we can rewrite this equation as p of r is equal to p naught plus 16q square by pi square into 1 by capital R square minus 1 by small r square. And this is the final expression that we get. Unfortunately, none of the answers match the options that have been shown here. I don't know why that is. I think there is an error, but this is the final answer that we get. I have checked this with Professor Sumesh Tampi, and he has also validated my answer and said that this is the answer we are supposed to get. Apparently, there is some error with the printing, or not sure, but yeah, finally the answer will come to this here. Okay, let's move on to the next question, which deals with a pump that is shown in the figure. It's represented over here. Draws 220 meter cube per hour of water at room temperature from the reservoir, and this is the reservoir. The total frictional head loss is 5 millimeter. The flow discharges through a nozzle to the atmosphere, that's shown over here. Now we have to find out the velocity of the fluid at the surface of the water in the tank. So the velocity of the water at the surface, velocity of the fluid at the surface of water, velocity of water at the surface in the tank. So what we generally do is when we have a question that's based on a reservoir, we automatically assume that uh, the fluid in the reservoir is stationary, and therefore we can automatically write u is equal to 0 over there. Therefore correct answer is option A over here. Now again same question, the exit velocity that's coming out of the nozzle from here is being asked. So for that we need to find out the exit velocity, the flow rate at which it's being exited. And it's shown that the pump draws 220 meter cube per hour of water through the 12 centimeter pipe, and it should be understood that whatever is being drawn will in fact be ejected. There won't be any accumulation that's happening in the pump. So we can write that the flow rate at the exit should be equal to 220 meter cube per hour, which in SI units would be 220 by 3600 meter cube per second. Yeah, and this value will come to roughly 0.061 meter cube per second. Therefore, we can find the velocity at the exit to be equal to the flow rate at the exit divided by the cross-sectional area, that's given by pi by 4 e square. And okay, as given in the question, this is capital D as shown here. So we can write that as 0.061 by pi by 4 times 0.05 square. We'll get the exit velocity here as 31.1 meters per second, which is the same as option F as shown here. Okay, so the next part. Okay, next part we have to find the pump head in meters, and the pump head in meters has to be obtained from the Bernoulli equation. And in the Bernoulli equation in head, or we have to write that in pressure heads, or this is called as heads. And the Bernoulli equation in this manner is written down as P1 by rho g plus V1 square by 2g plus H1 plus, let's say, any pump that's coming out, that's doing some work, should be equal to, this is the this W pump is the pump work in meters, or pump head that we need to find out. We just equate it to P2 by rho g plus V2 square by 2g plus H2. And we know that if we consider this as the datum, then H1 is 6 and H2 is 8, since this is 2 meter above it. But if we consider this as the datum, H1 goes to 0 and H2 is not 0, H2 is sorry, H2 is not 0 and H2 is equal to 1 second, yeah, H2 should be equal to 2 meter. And we have established that the fluid is stationary at the reservoir at the surface of water. We can assume that the pressure over here in this surface is the atmospheric pressure, and it is given that the flow discharges nozzle to the atmosphere. Therefore, sorry about that. Yeah, therefore, P1 and P2 are in fact equal to the atmosphere. Now we can just write down, we have just found out what the exit velocity is, that comes to around 31.1 meter per second. We have all the data we have. In order to solve this, we can just find out the pump head that is given here. It should be equal to 31.1 square by 2 into 9.81 plus H2, that's 2. And also I have forgotten there is a frictional loss that's associated with this, and the total frictional head loss is 5 meters. So the head loss acts opposite to the work of the pump that's done, therefore it should be in the opposite direction, or on the other side of work pump. So there will be another plus 5. Finally, you will get this answer as 56.29 meters. Okay, let's move on to the next part, where it's given to estimate the pump power in kilowatts. How do we move from pump head to pump power? You know that the pump head we just found out, uh, I'll just denote this as pump head, should be equal to 56.29, yeah, 29 meters. Therefore, the work delivered by the pump should be equal to, you have to convert this into rho g. Yeah, you have to multiply this with rho g to get the uh, pressure head, and multiply it with the flow rate to finally get the work delivered or pump power in kilowatts. And this would come out to the following substitution. This would be 1000, this would be 9.81. Pump head we have just found out that 56.29, and we found out the exit flow rate as 0.061 meter cube per second. From here you'll be easily able to find out the value of the pump work, which will come out to be approximately 33.75 kilowatts. Okay, let's move on to the next question. In the usual notations of one second. Okay, in the usual notations of cylindrical coordinates, usual notations of cylindrical coordinates, what are the values of the following? Where theta is defined from the x-axis in the counterclockwise and direction in the right-hand coordinate system. What is the dot product of theta cap with r cap equal to? We know that in every coordinate system, all the axes are orthogonal. Means that if you have a radial direction here, the angular direction that is mentioned here should be meeting at a perpendicular point over here, such that this angle usually will be 90 degree. Therefore, a dot product between the theta cap and r cap will always be equal to 0. Yeah. So, I think this question is incomplete. But what they have asked is, in the usual notations of cylindrical coordinates, what are the values of the following? What is theta cap equal to in terms of cos theta and sin theta and ur and ux and uy? Now we just have to fill in the blanks here. Theta cap is dash x cap plus dash y cap, and we saw that earlier that theta cap is in fact minus x sine theta x cap plus y cos theta. Sorry, just take out that page. Yeah, this one. Theta cap will be equal to minus x sine theta plus this will be y cos theta. This will be I cap and j cap. Okay, let's move on to the practice problems for week 2, and it is again repetitive of what was given in the graded assignments. This is the practice problems refers to the ungraded assignments, and all this is almost the same question that's been asked here. The only thing different is that we have to find the terminal velocity rather than the angle of inclination, because angle of inclination is given as 15 degrees. Therefore, just as we did before, we can write Wg sine theta should be matching with the shear stress at the wall, mu v by h times the area. From here, we just need to find out what the velocity is. And v is equal to Wgh sine theta by mu a. And by substitution, the every other value remains the same. 6 into 9.81 into 1 millimeter thick film times sine of 15 degrees divided by 0.29 times the area, 0.0035. You'll finally get this value as 15 meters per second, which is exactly the same velocity that was described in the first problem of the graded assignments. The rest of the problems also are very similar, which is just the number that has been changed here, and Baki sub remains the same. So we can see that a pump, the exact figure has been shown here, is shown that a pump in figure 6 draws 100 meter cube per hour of water at room temperature. From the reservoir, the total frictional head loss is 10 meter, and the fluid discharges through a nozzle to the atmosphere. The discharge diameter is also given. Velocity at the at the surface of water in the tank can be considered as 0. The exit velocity is in fact q by pi by 4 dE square. Except for the value, except for the numbers, nothing else changes. So I'm gonna leave this calculation to you. The pump head again we can calculate by equating the v square by 2g, v2 square by 2g plus let's just say notice ve square by 2g plus h height in the vertical direction plus the frictional head loss that is mentioned over here. And the power in kilowatt delivered can be found out from the pump head as pump head times rho g times the flow rate. I'm gonna leave this part of the calculation to you. If you have any doubts, please feel free to ask. If you still want any clarification, I am there to help you out. Okay, we have done the graded and non-graded assignments for week 2. Let's just quickly go through what's been discussed for week 4. And the week 4 topics are the non-dimensional analysis and Buckingham Pi theorem. So the main importance of these non-dimensional analysis is to figure out an equation or find an equation that is independent of uh, or not actually dependent of the fluid property or properties, and or we can just characterize it using certain non-dimensional numbers that can typically be used to define the flow rather than the entire and the fluid. And the Buckingham Pi theorem will help us to get some idea of how to scale stuff. Like, for example, if you are doing on a lab scale and you want to promote it to an industrial scale, what should be the multiplication factor or what should be taken into consideration in order to achieve such a scale up or scale down that is required to facilitate the process. With that said, we'll just quickly do two questions based on the Buckingham Pi theorem. These are example questions from relevant textbooks such as Sengel or Bansal or Method Smith and everything like that. So yeah, let's just get started with the question that starts with a story. Actually, some children are playing with soap bubbles, and you become curious as to the relation between the soap bubble radius R and the pressure inside the soap, that's P. You reason that the pressure inside the soap bubble must be greater than the atmospheric pressure outside given here, then that the shell of the soap bubble is under tension, much like a skin of a balloon. You also know that the property surface tension sigma must be important in this problem. Not knowing any other physics, you decide to approach the problem using dimensional analysis. Establish a relation between the pressure difference delta P, the soap bubble radius R, and sigma S, surface tension sigma S. So we'll just start off this particular term as any other, where we can write delta P is a function of uh, the soap bubble radius R and the surface tension sigma. And you know that the pressure has the we need to find out dimensionally how to analyze this. So we dimensionally split the pressure as force per area, and you know that force is kilogram meter per second square upon area, and this will be m l raised to minus 1 t raised to minus 2, where m, l and t represents the mass, length and time in the dimensional form. Similarly, the drop radius is just can be written as L, and the surface tension can be uh, written as force per unit length, that is ml t raised to minus 2 by L, which is m t raised to minus 2. Now all we have to do is we just have to find out how to equate these three. This has nothing to do with Buckingham pi theorem yet, but we just have to understand from dimension analysis how delta p is related to the drop radius and the surface tension here. And just by analyzing, we find that um, A should be equal to minus 1 and B should be equal to 1. Therefore, we can write this as mt raised to minus 2 L raised to minus 1. And that will match the pressure, the dimensional analysis, dimensional formula of pressure as ml raised to minus 1 and T raised to minus 2. Therefore, we can conclude that the pressure difference must be the surface tension divided by the radius of the soap bubble, or times some constants of equality. And this is in fact coming out to be true. See, we know that for a soap bubble or for a drop, we'll get this as 2 times sigma by r, and for a soap bubble, we'll get this as 4 sigma by. And this is just something known as the capillary pressure inside a bubble or inside a drop. And we have already seen this since our 11th and 12th standards. So this is very fairly straightforward and understandable. If you have any doubts, please let me know. Okay, let's just take a look at one more problem before we leave. And this will be on the Buckingham pi theorem, where it stated that consider the flow of an incompressible fluid of density rho. This is not r, sorry for that. This is in fact rho viscosity, it's not m, it's mu, through a long horizontal section of round pipe of diameter d. Velocity profile is sketched, actually that's not shown here, it's fine. V is the average speed across the pipe cross section, which by conservation of mass remains constant down the pipe. For a very long pipe, the flow eventually becomes fully developed, which means that the velocity profile also remains uniform down the pipe. But because of frictional losses between the fluid and the pipe wall, there exists a shear stress tau W on the inside pipe wall. The shear stress is also constant down the pipe in the fully developed region. We assume constant average roughness height epsilon along the inside of wall of the pipe. In fact, the only parameter that is not constant down the length of the pipe is the pressure, which must decrease linearly in order to push the fluid through the pipe to overcome friction. Develop a non-dimensional relationship between the shear stress tau W and the other problems in other parameters in the problem as V, epsilon, rho, mu, and d. So we first write down what tau W is as a function of V, epsilon, rho, mu, and d. And we'll write down the dimensional analysis of each of them. So tau W will be in the units of ml t raised to minus 2. Sorry, this should not be the equation over here. This should be m l raised to minus 1 t raised to minus 2. And we write down the equations for the others as m t raised to minus 1, which is in meter per second. Roughness is generally denoted in the units of length, density in the units of kilogram per meter cube or ml raised to minus 3, viscosity in the units of kilogram per meter second or ml raised to minus 1 t raised to minus 1, and diameter in the units of length again. So let's go through how many independent variables we have first. That's is equal to m, l, and t, which is 3. And the see number of uh, variables in question, or this should be defined as j number of variables. Otherwise, total number of variables is 6 tau w v epsilon rho mu d, which is 6. Therefore, number of pi terms should be is equal to 6 minus 3, which is 3. So there must be 3 pi terms, pi 1, pi 2, and pi 3, and we have to define or decide which of these will come in which of those. So we have to follow the rules that were discussed in class by Professor Sumesh and just find out the values of each of them. We can assume that tau w, v, and epsilon are uh, properties of the or properties that can be established in the others three. And since epsilon and d are having the same dimensional analysis, we can't take both of them. We just have to prioritize being taken d as one of them and find the pi value for epsilon. So let's first take one as tau w and uh, multiply it multiply it with rho u rho mu and d. Let's use u here, or velocity v here. Now this will come out to be m l raised to minus 1 t raised to minus 2 times m raised to a l raised to minus 3a v raised to v is l L raised to b t raised to minus b meter per second, and d raised to this is from d, this will become L raised to c. Therefore, we can write in by clubbing the powers together. We can write m air plus 1 L minus 3a plus b plus c minus 1 and t uh, raised to minus 2 minus b. And we know that from dimensional analysis, we can write a plus 1 is equal to 0, minus 3a plus b plus c is equal to is equal to 1, and b is equal to 2. Therefore, we can get this a is equal to minus 1 from here. So 3 plus 2 is equal to 1, and therefore we'll get c is equal to 0. sorry, we'll get b as minus 2, therefore we'll get c to be equal to 0. Yeah, c equal to 0, that's correct. Therefore, we can write the first term as tau w by rho times u square or v square. And this is generally referred to as the inertial term or inertial dissipation term. Basically, there's a rho square by 2 that should come, but since it's the dimensional analysis, that by 2 does not exist over there. Okay, now we have found out the first pi term. Let's move on to the second pi term, that's on equating the viscosity to the density, fluid velocity, and the length. And here we'll get viscosity as kilogram per meter per second, density as kilogram per meter cube, velocity as meter per second, and distance as meters. Okay. Now again we rearrange this to get m power a plus 1, L power minus 3, a plus b plus c minus 1, and t raised to minus b minus 1. So we can write a plus 1 is equal to 0, minus 3a plus b plus c minus 1 equal to 0, minus b minus 1 equal to 0. So we'll get a is equal to minus 1. From equation 3, we'll get b is equal to minus 1. 3 minus 1 minus 1. So you'll get c should be equal to minus 1. Therefore, we'll get pi 2 to be mu divided by rho times v times t. And this we are very familiar with is the Reynolds number, which is actually Reynolds number inverse or 1 by Reynolds number, but yeah, you get the point where a non-dimensional number has directly been associated. Finally, we just have one more term pi 3 as epsilon times rho power a, b power b, and b power c. I think it is actually very straightforward, but I'll still do it where we can get a direct relation between epsilon and d. You don't have to worry about uh, the density and viscosity coming out, density and velocity coming out here. So what you'll get is m raised to a, m power a, L power 1 plus b plus c, and t power minus b. We'll get this as the equation. We'll get the final equation as a is equal to 0, b plus c plus 1 equal to 0, minus b is equal to 0. Therefore, finally you get c is equal to minus 1. And then you can find out pi 3 just by substituting here, which is epsilon by d. This is also known as the roughness ratio, where epsilon is the roughness and d is the diameter of the pipe. Therefore, we all have our pi 1, pi 2, and pi 3. We just have found out everything that has been asked of us. We have been asked to develop a non-dimensional relationship between tau w and all other parameters that have been in question here. Okay, so that's it for this week's lecture. If you have any further questions, I'll be happy to answer that. Please feel free to ask it in the forum on the website on yeah, the NPTEL SWAYAM website. Thank you for your attention. I'll be here a few more minutes if you have any doubts.